Welcome to Structural Dynamics class. So, in this class we will study about tuned mass damper. So, what is tuned mass damper? So, tuned mass damper is controlling the vibration of a structure or by using mass. So, the tuning is done according to the frequencies. So, there is a structure and this structure, the primary structure, so this has severe vibrations because of some given input. So, when vibration amplitude is more, so there will be safety issues to the occupants and comfort issues to the occupants. So, what we need to do is we need to control the vibration. So, tuned mass damper is tuning the frequency of the secondary structure which we are going to install either on the top or anywhere in this structure, and the frequency of that structure matching with the frequency of the primary structure, and using these two we will derive the damping which needs to be present in the secondary structure, because the damping already present in the primary structure is insufficient to control the vibration. So, this is the main concept of tuned mass damper. So, a tuned mass damper, or popularly called as TMD, is a device consisting of a mass, a spring and a damper that is attached to a structure in order to reduce the dynamic response of the structure. So, the frequency of the damper is tuned to a particular structural frequency, so that when that frequency is excited, the damper will resonate out of phase with the structural motion. So, let us look at this structure. This is type A 101 building, and on top tuned mass damper is installed. So, if you look at closely, it looks like this. So, this is a mass system hanging from this location, so in the form of pendulum. So, this makes the severe vibration out of phase, so that the total vibration or the maximum displacement will reduce. So, as you can see, this is the motion animation of it. You can clearly see that. So, in long span bridges also it is done. So, this is a exaggerated cartoon, so showing how the dampers are installed. Now, let us look at formulation part. In this formulation, you can see this is a primary structure on which a secondary structure is constructed. For explanation of concept, I have kept one additional floor, but it is not needed. It can be a very small component which is having some percentage of weight of the building. So, that weight can be 5% to 10% the weight of the building. So, this is called main structure, and this is tuned mass damper. And as you can see, this tuned mass damper acts like this. So, this is a conceptual explanation. So, this is primary structure, secondary structure. So, this secondary structure's weight or mass can be from 5% to 10%. Okay, in some cases it is even less. So, in this one, primary structure's stiffness, primary structure's damping. So, this is approximately 0, it's not present or very less value. So, this value we have to find out, and mass and stiffness together will offer omega d, that is frequency, damped natural frequency of this system, and these two offer natural frequency of the primary system. So, tuning is done between primary structure's frequency and the secondary structure's frequency. So, mass of main structure M, C damping of main structure, K is the stiffness of main structure, MD is mass of damper, CD is damping of damper, KD is stiffness of damper, and U is the displacement, and UD is the displacement of the damper. Now, if we formulate the 2 degree of freedom system mass matrix, so this is actually, this M is n degree of freedom system, already this is n degree of freedom system, it is there, and the additional damper system is adding one more degree of freedom system. So, M 0 0 MD, U double dot and U double dot D, C plus CD minus CD minus CD CD, U dot velocity of primary system, velocity of damper, K plus KD minus KD minus KD and KD, U and UD. U is the displacement of primary system, and then UD is the displacement of damper. So, MUG double dot is a force acting due to earthquake ground motion, md into ug double dot is force acting on the damper due to earthquake ground motion. So the total equation of motion is mu double dot plus cu dot plus ku is equal to minus mu double dot g. So where m is mass matrix, compound mass matrix, C is damping matrix, compound damping matrix, K is compound stiffness matrix, U double dot is acceleration vector, velocity vector and displacement vector is U. When the support excitation is harmonic, its displacement amplitude is fixed and independent of input frequencies, that is U is equal to h e to the power of I omega t. So this is assumed displacement profile. This is in steady state response. If we take the displacement response, that is k into u vector is equal to the response vector. So as you can see, omega is a natural frequency, gamma omega d omega a I 2 omega a, all this complex notations, where omega is natural frequency of the primary system, omega d is kd by md, so natural frequency of the damper, and zeta value is a damping C by 2 m omega, and zeta d is this is zeta present in the primary structure, this is damping present in the damper, and gamma is a mass ratio, so md by m, so mass of the damper by damper. So now you know all these values. If we plug in this, we will get the ratio of displacement amplitude of the main mass to the input amplitude can be solved. So this is displacement of the main mass and this is input amplitude. So is this complex where frequency ratio is omega d by omega and g is omega a by omega. So optimum parameters for undamped system are harmonic main mass excitation. So F optimum is 1 by 1 plus gamma. So gamma is a mass ratio. So zeta damping, so damping of the damper optimum is 3 gamma by 8 into 1 plus gamma under root. Harmonic base excitation, so F optimum and zeta optimum values are given. So for optimum parameters for damped systems, F optimum is given and zeta optimum is given like this. So let's solve an example problem using these complex notations. So a single story, single base structure with planned dimension 7 meter by 7 meter and taken, and a tuned mass damper is designed for no damping condition. So that means what? When primary structure has no damping present in it, so we want to reduce the vibration energy or vibration amplitude by using tuning of second mass. So cross section of beams, columns, thickness of slab, concrete grade is given. So it is this is a structure, figure of the structure, and then let us calculate modulus of elasticity, that is known as 5 given in IS 456, that is 5000 under root FCK. So we know this value, and then moment of inertia along x direction and along y direction. So because it is symmetric in both directions, so this mi is same in both directions, and then calculation of the mass. So we take weight of the slab, weight of column, weight of beam and total mass. So 27,620 kg, and then natural frequency of primary system, so 74.15 radians per second, so that offers 0.08 seconds. Then assume mass ratio as 0.03, so that means 3% mass is taken. So mass of the secondary structure or damper is 828 kg. The stiffness of the damper is again 3% is taken, this one. Just we need to tune it now because we need to match the frequency, that's why same ratio is used in mass as well as in stiffness. So F optimum is 1 by 1 plus gamma, that is mass ratio, so 0.978, and zeta d, that is damper optimum damping value, is taken as say 0.1, so that will become 10% of damping. So stiffness optimum, damping optimum, if we calculate, so we get these values, and then so these values when we adopt and apply in the that compound mass matrix, stiffness matrix, we get the final response as a reduced response. So damping in the secondary system is helping primary system in two ways. Number one, it is changing the phase of the primary system, that means frequency, because of the frequency of the compound system is different from frequency of primary system. If frequency of primary system and excitation frequency matches, then it will go into resonating condition and amplitudes will become high. So because of the presence of the secondary system, so frequency is changed so that your frequency ratio compared to compound structure and excitation frequency is now either less than the original frequency ratio or more than the original frequency ratio. In both the cases, vibration amplitude reduces severely. So in summary, so we have studied how to design a tuned mass damper in this class.